Okay, so I'm going to share the screen, go back to the whiteboard. Okay, so as we were saying, so we're kind of working through HMM, right? So hidden Markov models, trying to understand this. Remember, this is sequential, as part of our discussion of sequential machine learning. So sequential machine learning. Okay, and we're talking currently about hidden Markov models and then leading up to reinforcement learning. Okay, so we were talking about the problem of predicting basically. I lost the whiteboard. Okay, so we were looking at the problem of predicting states. Right, in this case, rainy, sunny, given some observations, right? So in this case, the observations are going to be, walk, shop, clean, walk. Right, so if we think about this as what happens every day, so this is Monday, Tuesday, Wednesday, Thursday, then given this observation, we want to predict what is the likelihood given the state. So in this case, it would be for walk, shop, clean, walk, it should be sunny, let's say rainy, rainy, sunny. You see that? But there can be other variations of this. This one would be the correct one, let's say. This one would be an incorrect one. And there are many combinations depending on how many states we have it set up, the length of the sequence and so on. But this model works for any sequence, so that's a great thing about it. So this problem then of predicting this can be modeled as a Bayes problem, and a probabilistic problem based on Bayes' theorem. So the formulation, as I said, we can use Bayes' theorem to formulate this problem. So Bayes' theorem is basically written out as A what is the probability of A given B? And this basically can be written as the probability of B given A times the probability of A divided by the probability of B. That's Bayes' theorem. And actually, it's quite important because if you think about it, our original problem is this one. I have observation, walk, shop, clean, walk. I want to predict correctly sunny, rainy, rainy, sunny. Okay, so if we think about it, we use Bayes' theorem to write this out. So I'm going to say then, well, what I want is, what is the probability of rainy, sunny, sunny, rainy, right? Or another probability could be the probability of sunny, rainy, rainy, sunny, and so on, multiple ones, right? So I'm just going to grab one and say, I want this sequence given the other sequence, which is, walk, shop, clean, walk. You see that? So that's the correlation there between Bayes' theorem. So A is what we're trying to predict, B is the condition. So if you think about it, then we write this out here as this equation. So then this becomes the probability of what is B. So walk, shop, clean, walk, given A, which is rainy, sunny, sunny, rainy, right? And we're going to repeat this. This is just one, this is two. So we're going to repeat this for every single combination and then pick the highest probability. So we are writing, so PBA is this one, right? PA now is going to be what? The probability, A is this one, so of rainy, sunny, sunny, rainy. right? And then we divide this by the probability of B, which is walk, shop, clean, walk. If you think about it, we would do this for this one as well. Walk, shop, clean, walk. Probability of walk, shop, clean, walk. Now the sequence is S, R, R, S. Probability of R, S. Well, it's a, sorry, I got this. No, it's correct, right? What did I do wrong? Oh, sorry, yeah. So this one is different. So I was looking at, so R, here is SRRS. So SRRS, this one needs to be, sorry about that. So this would be SRRS divided by, what's it divided by? Probability of walk, shop, clean, walk, correct? But yes, right? Now, remember, we just have to pick the highest one of the two. Both of them have the same denominator, right? So you have like A half, B half. Isn't this something like half A, half B, right? So what can we do to the denominator? Get rid of it. Do you guys see that? And so since we can get rid of the denominator, it simplifies this considerably, because really it's the same thing. Walk, shop, walk, shop, clean, walk, walk, shop, clean, walk. So we can get rid of it. So that simplifies this considerably to just be then probability of walk, shop, clean, walk, condition on RSSR times probability of RSSR. And then over here, probability of walk, shop, clean, walk, given SRRS times the probability of SRRS, right? And that's what it comes out to. And so that's really great. The other simplification is, as I said, we don't have transitions that are this big, right? We don't have a table where we saw a sequence of rainy, sunny, sunny, rainy, and then what was the next fourth sequence one of walk, shop, clean, walk. That would be too difficult, right? Like the example I gave you in the previous video of the black hole gravitates towards. Getting that foreground would be very difficult in any corpus. So the other simplification that we do over here is that we can basically break this out into individual multiplications. Okay, so let me. So over here, I'm just going to do this. So now probability of walk RSSR, probability of RSSR, like that. We're just going to simplify this even further by saying, well, the probability of walk given R times the probability, oops, not there. Times the probability of R. You see that? Multiply times the probability of this one, right? Shop given sunny times the probability of sunny. Do you see that? This is much easier to get values that are meaningful for this problem. Times the probability of shop given sunny times the probability of sunny times the probability of walk given rainy times the probability of rainy. And that's it. That's literally how this would work. So Bayes' theorem is really nice to solve our big problem, right? And so now that we have this one over here, this is a lot simpler because all we need is we need a table of, if I'm walking, it's raining, a table of walking to rainy, a walk of the observations to the states, right? We need that one, the conditional probability. And then we need an individual one of just the states, rainy, sunny. Do you see that? So plus we need that start probability that I told you about, because when we look at the first state, we need to have some initial state. And so that takes us here. We look over here. Now we are ready, hopefully. So before I continue, because I'm about to get into the data, did you guys understand Bayes' theorem and how it helps us to formulate our problem? Are there any questions about that? No questions? All right, so let's go then here. And now we are ready, right? So if you understood, you know what you need. Based on this, we know what we need, right? We need the probabilities from our corpus or our data set. So I'm going to go over here, and now we can actually define the problem very clearly. So we're going to say here, we need states, and they're going to be established as rainy, sunny. We need observations, which will be walk, shop, clean, and walk again. So we end up with basically observations can be three things, but the sequence is of 4 here. But there are 3 basically possible things that you can do in the observations, and there's 2 states. Okay, so now we need then, now that we have this defined, we want to predict a sequence of states for this. So remember Monday, Tuesday, Wednesday, Thursday. So we want to predict sunny, rainy, rainy, sunny, but we have multiple options. So now we've framed what we want over here in this. So now we just need the tables, and then we compute the equation. All right, so the first one is the start probability. So let's call it start probs. And that's going to be the probabilities basically. So this table just says what? If it's, so these are the start probabilities. So if it's rainy, or let's say the probability of it being rainy as the starting state is 0.6. Okay, and the probability of sunny is 0.4. You see that? That's it. So that's how you get those probabilities. Those will be the first ones just in the first state. Okay, then we need what are called the transition probability. So I'll do it over here. Let me change color here. So the transition probability is going to be the probability of going from one state to another. So I'm going to say rainy, sunny, and then rainy, sunny over here. So here, for instance, from rainy to rainy, there's a 0.7 probability. From rainy to sunny is 0.3. from sunny to rainy is 0.4, and from sunny to sunny is 0.6. Do you see that? These are the actual probabilities that we will use in our problem. We've computed these, and these help us to get, what's the probability of it being rainy, given that the previous one was sunny. So in this case, the way that this should work is something like this, where we say, well, let's say that we actually went, the way that I wrote this out, I did it like this, right? So if I change to a different color, you'll see that I actually kind of went like this and like that, right? That's kind of the order that I used here. Do you see this? So it kind of like starts here and it's accumulating until the end. All right, so basically what you're saying is the probability of sunny given that it was rainy. Got it? And then the next iteration, I'm going to change color here. The probability of sunny given that it was sunny before. And then I look at the next probability over here and I say the probability of rainy given that it was sunny before. Notice that they are now not looking at the whole sequence, they're only looking at individual ones. This is what makes it a lot simpler. This is captured by this simple table here that you compute. Okay, guys? And you have to account for this in the algorithm, basically, which we can use the Viterbi algorithm for this. And then the last part of this is the, so we needed what is called a start probabilities statistic. That's number one. Then we need number two, the transition probability from state to state. And now there's one final one called the emission. There's one final one called the emission probability, right? And the emission probability is the one that accounts for this part here. That what's the probability of walking given rain? What's the probability of shopping? Was this shop? No, clean. Yeah, shopping, right? S. Yeah, shopping at so given sunny, and this is the probability of clean given sunny, and this is the probability of walking given rain. So observation to state. Okay, so this one also we can get in the emission probability. So in our case, the emission probability will then look like rainy, sunny, right? And then, oops, let me redo this. Okay. Let me redo this. So I'll do it kind of above here. When I get too low, the mouse doesn't, or the pen doesn't work as well. All right, so rainy to sunny. Like that. And then here we have, so we have the rainy and sunny are the states, but now we need the observations up here. So that's going to be then walk, shop, and finally clean. So if you notice here, remember, we're doing a sequence of 4 things, but there are only 3 observations. We could do a sequence of 6 things, right? Or whatever we want. That's the beauty of this. I can predict what you're going to do, right? So I can predict when you're going to shop, when you're going to go to the movies. I have with your Fitbit or whatever, I know what you're doing sequentially, given, or what let me actually rephrase that. I am more likely to know. I know what you're more likely to do, right? And so now I have this one, this of course. So now we have this statistic as well, and the emission, this is called the emission probability. Okay. And so I'm going to say, so rainy to walk is 0.1. Rainy to shop is 0.4. Rainy to clean is 0.5. Notice that clean is the most likely given rainy. Notice also that these add up to 1. Okay, I don't know if you've noticed that. And then sunny to walk, 0.6. Sunny to shop is 0.3. And sunny to clean is 0.1. Again, they add up to 1. Now I have my statistics, which I got from the corpus. I know the sequence that I want, and basically I know what I need to do. Now remember, you have to do this for every single possible observation state, right? So in this case, we want to predict given the observation states, right? So we have to do it for every single one, okay? And then we're gonna pick the one that has the highest value, okay? Got it, guys? Is this making sense? All right, so that's the formulation of the problem right there. So we're done with the formulation of the problem. What comes next is, given this information, now we have to solve it, right? So we have to solve it. So now what I'm going to do is I'm going to switch from here. So I'm kind of done with the theory. So hopefully that made sense. And now let's look at the code, okay? So for this, I'm going to need to go to Scholar, right? So we need to go to Scholar. Okay. And we're going to run our program. Just give me a second. All right, so let's switch over to Scholar. So all right, so you guys can see Scholar now. Just make sure I have the screen here. Okay, so the next thing we need to do here is we'll need to we need to download the code, right? So I'm going to download the code. I'm going to open up Firefox. Okay. Opening up the browser. Right, and we're going to go to the code. And I'm just going to download it from this repository, Machine Learning Foundations. I'm going to download the zip. That's where I have that. Okay. So now we can go to downloads. Did you miss where I went? Oh, sorry. go to the web browser, and then you have to go to the GitHub. So here, right, and then go to code, and then here in my GitHub under Machine Learning Foundations. Yep. So just download that one. And then if we look at the downloads, it's right there. So let's just uncompress. This is so we don't have to type it. All right, so here it is. And then let's just move it to the class, but it's going to be this one under HMM. It's self-contained, so you can just grab this script basically. So copy it and then put it in the desktop on the semesters. We'll probably create and call this one HMMs. Remember that although this is sequential machine learning, this is only HMMs. This is not reinforcement learning. So in this case, we're only looking at hidden Markov models. So under that, I'm gonna paste the file, and there it is. Okay, so I've done that. Let's go ahead and close this. All right, so now we can open up a terminal emulator, and let's just navigate onto let's navigate to desktop. Okay, and let's navigate to the folder. Okay. Right, and then let's navigate to hidden Markov models. Okay, so here we are. We have the script. Basically, it should run on Pi 35. Okay, so I'm going to start bash. I mean, I tested it on Pi 35, I guess. Could run on other versions. Let's do this really quick. Okay, so now before we start describing it, let's just run it and make sure that it works. So I'm going to do clear. This doesn't really need that many libraries. So Python 3.8 here. I do conda environment list. We've got a Pi 36 environment. Let's go into that one actually. So let's do conda activate PyTorch Pi 36. But like I said, we don't. This example does not need any libraries. Actually, I've written it in not a very Python-y way. Instead of, so it's not the most efficient, but it is clear. It's the clearest, I should say, that I could write it in the most simplified way so that it all makes sense. Okay, guys? All right, so let's take a look. So the script is there. So the first thing, let's do it. Let's see if it runs. Pi 35. And it does run, so that's good. So it should run on the PyTorch environment that we've been using all semester. You can see it actually did run, right? So in this case, for instance, I give it the path walk, shop, clean, walk, and then its output is sunny, rainy, rainy, sunny. Do you guys see that? Which is basically what we wanted. Now, you can see here, there's a lot of information that's, you know, the tables, etc., that we talked about. So now now we know it runs. So let's go ahead and take a look at the script. So I'm going to do clear here. And nano 535. Okay. So this is the hidden Markov model implemented with the Viterbi algorithm. And I tested this with Pi35. Basically, all I'm using is NumPy and not much of it actually. So it's pretty simple. Notice that this is exactly like what we had discussed in the problem in the whiteboard. Notice the code is not very long actually. So I'll basically give you a high overview of it first. You can see here we print the observations, right? So we print the basic observations that we've discussing, and then we run the example. So example basically just calls the Viterbi algorithm, and it provides the observations, the states. It provides the starting probability, the transition probability, and the emission probability, which are the three things that I described, right? So if you remember in the whiteboard, I described transition probability, emission probability, and the starting probability. These have to be given as they are here on the whiteboard. So they're basically just dictionaries in this example. We give it the states, rainy, rainy, sunny, and then we give it the observation that we want, walk, shop, clean, walk. So it has to infer sunny, rainy, rainy, sunny. Okay? So this information in this slide is what is written in the code itself. So if we go back, we can identify it. So again, Viterbi, the observations, the states, start probability, and so on. So then Viterbi is something that, of course, was defined here. So it's the heart of this is the Viterbi algorithm. And you can see that located. Basically, it starts here. It's actually shorter, but I just added a lot of comments. Okay, so you can see Viterbi is this. That's the Viterbi algorithm. And then we'll look at this in a second. But this is the whole structure. A lot of it is just my comments in there. And at the end, it returns a probability and it returns the state sequence. So sunny, rainy, rainy, sunny. Okay, guys? Now over here, above the Viterbi algorithm, I really just provided a function print table, which prints out the V. V is basically a structure that's created in Viterbi to kind of solve the problem. All right, so that's what Viterbi is doing, is creating this V matrix. And with this V matrix, it's going to try to solve the problem. Okay. But that function basically does not serve a lot of it's not required, is what I'm saying. It's basically just there for you to view what the Viterbi algorithm is computing. And now we go to the top part, which is really where we add our observations. So rainy, rainy. There's the states. Notice I have 3 observations here just because I wanted to try different things. So I have walk, shop, clean, walk. Then I have shop, walk, walk, clean. I have clean, 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 walk. Right, just to see the different outputs. But these, we're just using this one. Here we have the start probabilities as we discussed. And notice rainy is 0.6, sunny is 0.4. Here we have the transition probability. So that is rainy to rainy is 0.7. Rainy to sunny is 0.3, sunny to rainy is 0.4, and sunny to sunny is 0.6. Do you see this? Any questions? And then here we have the final one, the emission probabilities given. So if it's rainy, do we walk? So rainy to walk is 0.1, rainy to shop is 0.4, rainy to clean is 0.5. Then from sunny to walk is 0.6. Sunny to shop is 0.3, and sunny to clean is 0.1. Okay, so basically what's in the slide, we just plug in, okay? And they're just basic dictionaries. So now that we have all the data, we basically just give this. We give the states, the observation, and these 3 probabilities to the Viterbi algorithm, and the Viterbi algorithm will do everything for you. Okay, so the Viterbi algorithm, given those 5 inputs, will follow its logic and output this sequence for you and solves it. Okay, so now, so obviously then that means we have to kind of go over the Viterbi algorithm. Okay, so we can skip this part. As I said, that's just a print table. And now we take a look at what's going on. So remember that what the Viterbi algorithm needs to do is what we had designated in one of the slides. So if we go back, the Viterbi algorithm uses this information, but it has to follow this logic. This was the logic, the Bayes theorem logic is what tells it what must be done. So remember, it must calculate, given walk, shop, clean, walk, all these sequences. Is it rainy, sunny, sunny, rainy? Is it sunny, rainy, rainy, sunny? Is it sunny, rainy, sunny, rainy? Is it rainy, sunny, sunny, rainy? You know, all of those, right? So we looked at the framework of the theory, all the simplifications, and for each one of those, let's say this one, number 1, we calculate this sequence like this, and it's going to give us a probability. Then, given these probabilities, we pick, you know, the best one, the most likely sequence, and that's going to be the correct one. Okay, so remember that this that you have here in the slide is what the algorithm must do. So the best way to look at it is to go slowly. So here is the Viterbi algorithm. So first we provide all the parameters. Okay, then the Viterbi algorithm basically creates this object V. This is an internal table that it uses, that it wants to compute values for. Okay. And these values are basically what it is. They're the cumulative values that are going to be used to predict the correct sequence. Path is basically a dictionary, but in here it's going to be plugging in, you know, kind of a list of the states that it should use. Okay, so or sorry, the final state sequence. That's the best. It kind of keeps track of all the sequences, and then it's going to pick the best sequence. Any questions? Right, so that's the idea. So let's, before we continue, let's run it. So you can see here, I printed some of these. So let's look at the output, right? So here's the observation. Here's the initial path in the first step. And then you can see how it starts to create these paths, right? Is it sunny or rainy, or is it sunny, sunny? Then is it sunny, rainy, rainy, or is it sunny, sunny, sunny? So these are the different iterations and how the path is being filled in. Finally, at the end, it has sunny, rainy, 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 or it has sunny, rainy, rainy, sunny. Do you guys see this? So it starts to create these individual paths. At the end, it computes a final probability, 0.002, and that's the probability, the highest probability for the given sequence. Okay. Internally, it starts to compute this V, which is a dictionary, and I just wrote it here as a NumPy matrix, so it's easier to see. So here we have rainy, sunny, and it's keeping track of the probabilities of how it's going, okay, of the sequence. If you notice something that's interesting and obvious here, notice how these probabilities are cumulative. Notice that in the first, so these are the probabilities also for each observation, right? So this is going to be like walk, shop, clean, walk, right? So these are the 4 observations going down, and these are the 2 states. If you notice here, in the first observation, the probabilities are high, 0.6 and 0.24. That's a very high probability. But as it starts to go down, because it's multiplying, right? Remember, it's doing that, right? It's multiplying. So that would be the first one, then the second one, then the third one, and the fourth one, right? Do you guys see this? For the 4 observations. So basically here, it's doing that there. So the first one, the second one. Notice at the end, the last one, they're very tiny. They're only 0.0009 versus 0.0024. And notice that between 0.0009 and 0.24, this is the highest one. So that's the one that it picked for the given sequence. Is this clear, guys? Are there any questions? No? All right. So now let's get into some of the details of the Viterbi algorithm. All right. So we know that we have the states, the probabilities and everything. Then we come into the algorithm. That V matrix that I just showed you is basically the probabilities, the cumulative probabilities that it's calculating for every state, right? And the sequences. And then this is the path that it's accumulating. So the first step is to do the first observation, okay? So the first observation has to be different because you're at the first one, so there is nothing before you. So at this junction, you have to use the initial probabilities, right? If you remember, you use the initial probabilities. So here, notice to calculate the V value, right? You have this V value will have 1 and then the other observations here, right? The cumulative ones, cumulative values. But this is only the first one is populated. So the way this is calculated is you're going to look at the start probability given sunny or the start probability given rainy. Okay, but if you remember from the equation, you also need the emission probability of sunny given whatever the observation is. So the first observation is walk, right? So you would choose from the table the walk observation. You see that? So this would be sunny walk. So probability of sunny walk times start sunny. So if you look then, so sunny walk times sunny start. So if we go here, we're going to look up sunny 0.4, right? And we're going to look sunny walk, right? Sunny walk 0.6. So 0.6 times 0.4. That's the probability that we calculate there because that's the state that we're looking at. Okay, guys? So this is what we want to compute. Okay, so we start to calculate these probabilities there. Then on the other end, we do the probability of rainy and the probability, the emission probability of rainy given walk, right? So rainy given walk and rainy. So we go over here, of rainy 0.6 and of rainy walk 0.1. So 0.1 times 0.6, we calculate that probability, right? And that's how we start to accumulate for all of these possible paths so that we can select a maximum one. Okay, so here we start then accumulating the values. So in the for loop then, we have, the different states, right? So the different states are rainy and sunny. And we're gonna, basically what we did here, we compute with this. We just repeat it, right? So we do this for rainy, and then we're gonna do it for sunny. But you can see it's the same idea as up here. Okay, and then we're calculating these in the first node of V for rainy and for sunny. Okay, and then we start accumulating also the possible path that we would choose here. Okay, and so that's the first step to populate the first observation. After that, we have one for loop for the other three, because the other three are kind of don't need do not need this one anymore, the start probability. Okay, guys? So the start probability is only needed in the first observation. Now we're going to calculate the other three observations for shop, clean, and walk. So these three, that would go here in this one, and that one. We need to now populate those. Okay, but it's exactly the same thing we did for the first one, only we do it now or the other one. So this part of code, this other for loop says, now look at the other observations, excluding observation 0. Notice the range starts from 1, not 0, right? So we're no longer looking at observation 0, we're starting at observation 1. And then observation t here is an integer index for the observation. So we look at the for loop. Notice it's 4 in range from 1 to the length of observations, which is 4, right? So we're just going to do the other 3 observations. So we did already walk. Now we look at shop. What was it? Shop, clean, I think, and walk again. Those 3 other states. And we're going to compute the values. So here we have, again, the new path that we have to compute, and we also have the internal Viterbi matrix, which is basically going to be a list where we're going to add our probabilities, our cumulative probabilities. So here, this is basically, this for loop here is the heart of Viterbi. Okay, this is going to be the heart of the Viterbi algorithm. So at current observation, calculate the probability per state. Okay, so again, we're going to repeat for the 2 states, which are sunny and rainy. Okay, and we have a list of probability states that we're going to accumulate. And then now here, we need to repeat this for every, we create another for loop for state, but notice it's y0 in states. This is because we need a multiplication here that's going to be from sunny to sunny or sunny to rainy, right? So we kind of need to have this additional for loop to account for that, for this table. See this table here, this table here from rainy to rainy, rainy to sunny, sunny to rainy. We need to calculate this, right? And so we need to basically have that additional for loop in there for that. Okay, this one here. Notice both of them basically go over the 2 states, but this second one allows you to create that. So now here we have the computation of the probability. And you will notice this is basically nothing more than the previous observation probability times the state-to-state probability times the state-to-observation probability. Do you guys understand that? If I go, if this is it. That's the heart, the meat, whatever you want to call it, of Viterbi. If you, or actually I should say a Bayes theorem. So if you go back here, basically what that means is, think about it. We already computed this one, correct? Do you guys agree that we already computed that one? That was done in the first observation, the first for loop, right? So if I bring this over, let me change color here. The yellow, okay. So this is done in that for loop when we use this one. Okay, we use that one, right? So that for loop used that one. We've got it calculated. Oops, sorry. Now we are in the second for loop where we need the previous one. We also need the state one, and we need the state to observation. So that means the emission, the transition, and the previous, right? Then in the next iteration, we would have calculated the whole thing. So then we would need emission, transition, previous. Do you see this? Then in the next one, note, imagine the yellow line extends to here. So then we would have emission, transition, all yellow is previous. And we're accumulating it so that we can arrive at the final one. Okay, so basically this idea is captured in that code as such. Previous observation, state to state, state to observation. which are, as I said, you know, those different named tables. You know, transition emission. Okay, so here we look at the code. We can see that we already computed the previous in V, right? The previous are all, that's why we keep track of V. V is just keeping whatever previous probabilities we capture, we put them in there, and then we can reference them ideally. Notice that observation up here, observation T, is a index. It's an integer from 1 to 3, basically, because we have 0, 1, 2, 3. So we are at 1, 2, and 3 observations. So then we go over here into that for loop and notice V observation T minus 1. What does that mean? We look at observation 0, right? Because we are currently on observation 1. And then we calculate the values for the individual states that we have 2 of. So we say, get the probability of in V of row 0, column 1, and column 2. Okay, so that's why we do it in a for loop, and then we calculate. We take that probability, and now we're going to calculate the current one. So we look at the transition probabilities, which is state to state, basically, right? So here we're going to say, notice. This is a state and this is a state, just so that we can get the individual combinations. So this is going to be, the states are rainy and sunny. So this is going to be sunny and sunny, sunny and rainy, rainy and sunny, you know. And we get all of those, and we're accumulating them with these. That's why we have these 2 for loops, so we can calculate them all the possibilities. And then this one is the emissions probability, which is the state to observation. So here we're going to do for every state the given observation that we have. In OBS, notice that OBS is the input this one. OBS is that one, and that when we call the Viterbi algorithm, OBS is observations, and observations is basically these, right? So we're basically looking at, you know, if we say 0, we want walk. If we say 1, we want shop. If we say 2, we want clean. If we say 3, we want walk. Okay, we're grabbing the particular one that is pertinent to our problem over here. Okay, and so that's why, as I said, although this is probably a little bit hard, you know, to see the first time, this is the heart of it. Okay, so again, we're calculating these probabilities where we look at the previous observation. That's already captured in V. So let's say that we are currently in iteration 3. We are in observation 3. So then this is going to be observation 3 minus 1 is 2. We look at the results from the previous observation for the given states, right? We multiply that times the current one, which is 3, right? And so we look at all the different possible states from the transition probability, and then we look at, you know, observation 3 also. So whatever that one was, so I think observation 3 is clean for all the given states that we are iterating through in this for loop. Okay, and then that allows us to calculate the probabilities, right? And for every probability we calculate a state, and then we basically store these. So remember that we are calculating multiple paths, right? We're doing different combinations, right? So we add them. So every time we notice in this for loop, right? We do for loop, we calculate its corresponding probability and state, and then we append it to the list as a tuple. So every one of these combinations is a probability and a state combination. And then guess what we do here? What is that line there? Of all the possible paths that we've calculated, we select the maximum one. You see that max function here, guys? So that allows us to pick. So remember we said that we were going to pick the maximum probability. And so in list probability state, remember that it is actually a list of tuples where we have an associated probability, it's a number, and a sequence of steps, the maximum one. And then once we have that in this tuple probability and state, then we populate V again, because remember that we have now computed, let's say we were in observation 3, we just computed the probability of 3. And then we're going to use that in observation 4 by referencing V again. So we have to populate this, right? And so we calculate the probability, and then we just add the states to the new path. Okay? And that's basically the exact logic that we had described in the slide. So we perform the multiplication, we have possibilities, we select the maximum one for the state and the path, and that's basically it. At this point here, we can just print out the Viterbi object, and finally here at this code, just basically, as you can see, this code gets probabilities of last observation. Remember that the last observation is the final probability for the sequence, right, for each state, and picks the maximum one again. So we're going to go in, so you can see here, we look at all the different states, and from the Viterbi algorithm, we do length of observation -1. What is length of observation -1? 4 minus 1 is 3. There are 0, 1, 2, 3. So we select the last probability for each state, and then basically we do the same thing. We select both of them, we put them in the list, and then we just take the maximum. And that gives us the final result, which is the probability and the state. And that's it. So that's the Viterbi algorithm. So if you look, I'm going to now, we've described it. If I run it here, you can see I give it walk, shop, clean walk, and it gives me sunny, rainy, rainy, sunny. Now I'm going to try another one. So I'm going to go back to the script. Right now I'm trying shop, walk, walk, clean. What would you guys expect from shop, walk, walk, clean? Rainy, sunny, sunny, rainy, right? No, because the other one will take over. Yeah, so I could, but yeah. It's a good catch, but yeah. It doesn't accumulate it, it just replaces it. So think about it. So here I'm saying observations are these, and then here I'm saying, no, 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 they're these. So it's the same as doing that. Yeah. Yeah, so we said shop, walk, walk, clean is what? We said it was, what did you guys say? Rainy, sunny, sunny, rainy, right? Okay. So let's try it. So it predicted actually sunny, 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 rainy. So it missed one, right? Not, yeah, we may be wrong. It's right on the line. It's right on the line. Now we could play with this by changing that probability, right? What probability would we need to change? That if it's cleaning, no, what is it? If it's shopping, shopping could be more towards rainy, right? Okay, so let's do that. Shopping could be more towards rainy. So shopping. Let's see. Yeah, so you see they're very close, right? Shop and rain. So we can say 0.6. What were the values? I forgot. What was that value I just changed? Was it a 4 and 3? Yeah, so let's say 0.6 and 0.2. Let's see what happens. Did it fix it? It is now closer to what you guys thought, right? Because we did shop, walk, walk, clean, rainy, sunny, sunny, rainy. Let's see what did this to the previous one. So now we're going to uncomment this one. Now this one we do have to comment out. So clear it. All right, so it's walk, shop, clean, walk. So I would predict sunny, rainy, rainy, sunny. Sunny, rainy, rainy, sunny. You guys see that? All right, great. Let's try one more. Let's try this one. So this is clean, clean, clean walk. So that should be rainy, 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 sunny. Rainy, 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 sunny. There it is. Just had to fix one probability and it's more like the way that we think. Any questions, guys, on hidden Markov models? Does this make sense? No questions? All right, so as you can see, we applied this to a simple problem like this one. This could be applied to part of speech tagging, for instance. That's a much more complex problem, right? Now, I should say this is good for things like that, but not for language translation. Okay, because there's too much, you know, too many options, right? You know, let's say from English to Spanish, that's too much. But for part of speech tag, there's only a few part of speech tags, right? So it's like 20 of them or 30 of them, right? Adjectives, nouns, verbs, adverbs, determiners, that kind of thing. So it's good for that, for predicting. So for instance, when I gave you the example of you guys with your Fitbits or whatever, you know, what do you think companies want? They just want to know when they should advertise to you and sell you products, right? So they're going to look at your patterns. Oh, they're spending. Maybe they have money. Let's advertise right now. You know, they're you know, going out a lot. So that means they probably again have money. Let's advertise, but things about advertising. So it's basically, it's the way that you could describe this is like a supervised learning, but where the supervised learning is labels in a sequence. Do you see that? So it's kind of like that. It's like, you know, cat, you know, mouse, cat, dog, you know, something like that. But that makes sense in a sequence. All right, so that is basically all for hidden Markov models. This is the first of our sequential models, as I said. So hopefully it made sense. It's a very nice framework. So as you can see, kind of in conclusion, we have some kind of a problem like this, right? You know, we want to predict given walk. Hold on. Problem like this: walk, shop, clean, walk. We want to predict sunny, rainy, rainy, sunny. So we need two things for this. We need an algorithm, a scheme that's going to be based on Bayes' theorem, which I described over here and everything. And then once we know how to do Bayes' theorem, then we just need the data, the probability. So remember, we have the start probability, emissions probabilities, and transition probabilities. And then basically we solve this thanks to somebody named Viterbi, who came up with an algorithm. So we used the Viterbi algorithm. Okay, and this is basically what we wrote in that Python script. Okay, so that we switch over here, and that's you know, the one that I described. As you saw, it's not that long, and it can be written way more efficiently than this. I just wrote it this way so that it's a little bit more easier to understand than using list comprehensions and so on, or numpy arrays. But anyway, that's it. My recommendation to you guys is play with this script. I'm not going to assign a homework or anything like that, given that I want you to work on your term project at this point. But you have the code, it runs, you have it on GitHub. Maybe try other observation sequences of different lengths, etc. Play with it, read it. You know, maybe work it out by hand, right? The best thing that you could probably do is try to work it out by hand, convince yourself that it works the way that I describe it. On the exam, you might get the final exam, you might get some questions about this, but otherwise, there will be no homework related to it. All right, so as I said at the beginning of the class, we started talking about sequential machine learning. Today, we talked about hidden Markov models. We're almost out of time, so it doesn't really make much sense to talk about reinforcement learning in this lecture, but we will talk about it in the last lecture next Monday. So again, just to kind of summarize, so we did sequential machine learning, and there's two of those, hidden Markov models, and then reinforcement learning is a more powerful one. So today we covered this one for applications to part of speech tagging and just predicting sequences. In the next class, next week, we'll talk about reinforcement learning, and it's, you know, as I said in the motivation, applications to autonomy, basically, agents. This involves a bigger framework. However, you can start reading. So a couple of things you can do. You can start reading through this. Oh, it's in Scala, yeah. So you can start reading through. Yeah, so you can go to the course website, and I provided a chapter here on reinforcement learning. So my suggestion to you, although I'll go over this in the lecture next, let's just read through it. It's not that long. It's like 10 pages or 15 pages at most. And it really goes over the code. It actually, basically, it's written around a game, a very simple game called Frozen Lake. It's literally like this. You know, if you're a mouse and you want to get to the cheese, you start here, right? So then what are your options? You go here, right? If you go here, you fall into a hole, so you should go left, right? If you go left, you fall into the hole, so you should go up. If you go up, you're going to fall into a hole, so you should go left. If you go left, you're going to fall into a hole, so you should go up. And then here, if you go right, you're going to fall into the hole, so you should go up. If you go left, you'll fall into the hole, so you should go right. And if you go right, guess what happens? You get the cheese and you win. So very simple game, but this game we're going to use because it's pretty intuitive for understanding reinforcement learning. So my recommendation is read through this, be ready for the lecture next Monday, but just keep in mind, this can be applied to way more complex things like, as I showed you, aviation and so on. All right. Is that clear for everyone, guys? So that will be the last topic to discuss. So I hope you enjoyed sequential machine learning and hidden Markov models, at least to see the power of them. Reinforcement learning is even more amazing to me. I think if true AI ever comes from machine learning, it'll be around reinforcement learning somehow. So we'll cover that. Also, don't forget, so I'll probably do like the first half will be lecture, second half will be still the project. Okay, so be ready with your projects. Remember, you should be about 60% done with that term project by next Monday. I'll help you out, sit with you guys, and then after that, the presentations the following week. Any questions? All right, so we'll stop here for today, and I'll see you guys next Monday.